Will our galaxy get sucked into a black hole? Imagine this. Right at the heart of our galaxy lurks a monster. The supermassive black hole Sagittarius A star. In movies like Interstellar, it devours everything in its path. In memes, it's the end of the world. And every now and then the news hits us with, the galaxy is in danger. But is any of this actually true? Could it already be pulling us into its maw? Or is it all just cosmic clickbait? Let's break it down step by step. What exactly, whom, how, and where it can suck in. Or maybe not suck in at all. Ready to dive into this cosmic mystery? Hold on tight. It's going to be wild. First, let's figure out what kind of beast this black hole actually is. A black hole isn't some bottomless pit floating in space. It's simply a region where gravity, the pull, is so insanely strong that even light can't escape. Think of it as an invisible trap. Get too close to the edge, the event horizon, and that's it. You're in, no goodbyes. Inside, there's a point where everything gets crushed down to zero volume, and our normal laws of physics just break. But from the outside, it behaves pretty much like any super heavy object. It pulls stuff toward it, nothing more exotic than that. Right in the center of the Milky Way, our galaxy, sits Sagittarius A star, a gigantic supermassive black hole. Its mass is equivalent to about 4.3 million suns packed together. The mouth, event horizon, has a diameter of roughly 25 million kilometers. Sounds enormous, right? But put it in perspective. That's actually smaller than the distance from the Sun to Mercury. And here's a mind bender. If our own sun turned into a black hole, it would shrink into a tiny ball just 6 kilometers across. So yeah, on cosmic scales, this thing really isn't the terrifying monster people sometimes make it out to be. Point 1. Size and distance. Sagittarius A star is basically a pea in a massive stadium. The black hole is basically a tiny pea right in the center. And all the spectators, the stars, are sitting way up in the stands, dozens of meters away. That little pea isn't going to suck in the whole stadium. It just sits there in the middle, while everything else orbits around it, nice and steady. Our galaxy, the Milky Way, is an enormous disk stretching about 100 to 120,000 light-years across. Just to remind you, 1 light-year is the distance light travels in a year, roughly 9.5 trillion kilometers. Inside it, there are around 400 billion stars, plus tons of invisible dark matter, acting like cosmic glue that keeps everything from flying apart. The total weight of the galaxy? Something like 1 to 2 trillion suns put together. As we already mentioned, the black hole, Sagittarius A star, sits smack in the very center. And where are we? Our solar system is a whopping 27,000 light-years away from it. Light from there takes 27,000 years to reach us. So even if something wild happened right now at the center, we'd only see it thousands of years later. We, meaning our whole solar system, are orbiting the galactic center at about 800,000 kilometers per hour, like riding a giant cosmic carousel. One full lap takes 225 to 250 million years. It's basically a safe, stable orbit. We're not spiraling in or anything dramatic. We're just cruising in a nice circle, thanks to the perfect balance of gravity and motion set up by the universe's mysterious architect. Point 2. Gravity works exactly the same As for a normal star of the same mass, no vacuum cleaner effect here. One of the most stubborn myths out there. Black holes supposedly suck in everything around them way stronger than regular objects. A lot of people picture it like black hole equals cosmic vacuum monster that devours everything in sight. Nope, not even close. Sucking in, or more accurately, the gravity of a black hole, works just like regular gravity at large distances. Its special feature only kicks in up close, or more precisely, inside the event horizon. The event horizon of a black hole is its boundary in space-time, beyond which, or rather, inside which, the gravity becomes truly extreme. At distances much larger than the event horizon radius, the gravity of a black hole is identical to the gravity of any ordinary star or object with the exact same mass. Whether you use Newton's 1/r² law or Einstein's general relativity, same result at those scales. If tomorrow someone magically replaced Sagittarius A star with a regular, albeit gigantic star, weighing 4.3 million solar masses, the orbits of the stars in the galaxy would barely change at all. We'd keep circling the galactic center exactly the same way. Nobody would suddenly start plunging toward the center, because our orbital speeds are already perfectly balanced by centrifugal force. Only if something gets really close, within a few light hours or so, does hell break loose. Tidal forces start ripping things apart, spaghettification, gas gets heated to millions of degrees, X-rays go wild. But the vast majority of stars just fly past at a safe distance and never get that close. And us? Humans on Earth feel the gravitational pull from Sagittarius A star way weaker than the pull we already feel from the Earth beneath our feet. Point 3. Growth of the black hole. It eats like it's on a strict diet. Sagittarius A star is not a glutton. It slowly nibbles on gas and the occasional unlucky star that wanders too close, but the rate is ridiculously low. On average, just a tiny fraction of Earth's mass per year. We're talking a couple of Earth masses worth of material annually at most. Every now and then, there are binge episodes, like the famous bright flare in 2019. But those are rare exceptions. Compared to the real monsters in active galactic nuclei, the ones blasting out quasars and gobbling down hundreds or thousands of solar masses per year, our central black hole is basically fasting. Over billions of years, it has consumed less than 0.001% of the entire galaxy's mass. Most stars and gas clouds are way too far out on stable, circular orbits to ever fall in. And a lot of the gas that does drift toward the center gets blown away by radiation pressure, stellar winds, or magnetic fields before it can actually cross the event horizon, like food slipping off the plate before it reaches your mouth. Quick reality check. Even to eat just 1% of the Milky Way's total mass, Sagittarius A star would need something like hundreds of trillions of years at its current feeding rate. That's thousands of times longer than the current age of the universe. 13.8 billion years. Bottom line, our supermassive black hole is one of the laziest and most underfed in the entire cosmos. Point 4. The future. The meeting merger with Andromeda, our nearest big neighbor. Only in about 4 to 5 billion years will our galaxy collide with Andromeda. And even that word, collide, is misleading. It's not a catastrophic crash, but a slow, graceful cosmic dance. The two galaxies will gradually merge into one giant elliptical galaxy. Astronomers playfully call the future result Milkomeda. At their hearts, the supermassive black holes will circle each other for millions of years before finally coalescing. This union will send gravitational waves, ripples in the very fabric of space-time, shuddering across the universe like rings on the surface of a pond. Yet, despite the scale, the stars themselves won't explode from the impact. Space is vast and hauntingly empty. The chance of two stars actually colliding is like two ants trying to bump into each other in the middle of a vast desert. Instead, the cosmos will simply rearrange itself. A chaotic shuffle where new stars are born and the night sky is transformed forever. However, life on Earth will have reached its end long before this galactic union. In about 1 to 1.5 billion years, the sun's increasing heat will boil our oceans dry. Eventually, after another 2 to 3 billion years, the sun will fade, collapsing into a white dwarf. And what of us? If we survive that long, which is unlikely in our current biological form, we will have evolved. We will likely be post-biological, transcending these physical shells to migrate toward younger, distant star systems. In this grand timeline, the black hole at the center is not the threat. It is merely a silent witness to our evolution. All right, let's set these cosmic nightmares ablaze. Time to bust some horrors with a little fire. Myth number 1. It sucks everything in like a cosmic vacuum. Wrong. Gravity isn't magic. It's physics, and it weakens with distance. Unless you're teetering on the very edge of the event horizon, sleep tight. Believe it or not, our own sun exerts a gravitational pull on Earth billions of times stronger than that distant black hole ever could. Myth number 2. It's about to devour the entire galaxy. Again, nope. It would take trillions of years for the galaxy to fade away, and that would be due to particle decay, not a hungry black hole. Even the black holes themselves will eventually evaporate through Hawking radiation once they run out of energy. Myth number 3. The Andromeda merger is an imminent apocalypse. Not even close. Tidal forces are far too weak at these staggering distances. The universe is so vast that the chance of two stars actually hitting each other isn't even on the table. The only thing that will change is the view for whoever is there to see it. And let's be real, it won't be us in our current physical shells. The bottom line, laying the cards on the table. So, will it swallow us or not? Spoiler alert, no. Sagittarius A star isn't going to gulp down the galaxy. It's relatively small, we are incredibly far away, and our orbit is perfectly stable. It doesn't hunt, it survives on crumbs. It's not a monster. It's just the engine at the heart of our galactic home. Think of the Andromeda merger as a cosmic party. The night sky will blaze with the light of newborn stars, but nothing will be crushed. The real horrors? They are much closer to home. Our sun's evolution, the shifting climate, and the biggest threat of all, ourselves. What do you think?